afternoon, good evening, good morning, no matter where you are. Welcome to our webinar this week. So today is our great pleasure to have Marion Garçon speaking with us. So Marion got her undergraduate, master, and PhD education from the University of Joseph Lauria in Grenoble, France. And then she worked as a researcher in various institutions, like Carnegie Institution of Science, like ATH, etc. And now she is working as a CNRS researcher at the Clermont, France, and she has applied the various isotopic system into various sedimentary samples and pursuing questions that people not only in the sedimentary geochemistry community interesting, but also people in the hard rock community are very interested in. So today she's going to share with of her published work in Science Advances on the topic of episodic growth of felsic continents in the past 3.7 billion years. So Marion, please.
Okay, thank you for the introduction and thank you for inviting me to talk about my results about the growth of continents. So as you said, today we're going to be talking about the formation and the evolution of continental crust through time using the record of sedimentary rocks. So should I? No, it's not working. Yes, great. So just to start as an introduction, and so that we all start on the same basis, I would like to make a large introduction about the crust that we have today on Earth, and then we'll see what we know about the crust, the history of the crust through time. So you all know that today there are two types of crust on Earth, the continental crust, that is mostly on continents, and the oceanic crust that we find in the ocean. And these two crusts are very different in terms of area first. So the continental crust represents about 40% of the Earth's surface, and it's mostly emerged. This is a very important feature of our continents today. So you can see on this map that the colored areas correspond to the area of continental crust, and it's mostly respect the frontiers of the continents. And then in blue, there you have the oceanic crust, which is mostly below seawater. So the oceanic crust represents about 60% of the Earth's surface.
I'm sorry that I happened to mute you somehow, and I'm trying to request you unmute you, but it doesn't work. Too bad. Sorry.
Is it good like this? You hear me again?
Yeah. Now it's good. Yeah. Sorry.
Okay. Should I restart on this one? Is it okay on this slide?
Yeah. I think you can restart on this slide.
Okay. Good. So I was saying that the oceanic crust and the continental crust are very different in terms of area, 40% versus 60%. And also an interesting feature today is that the continental crust is mostly emerged, and this corresponds globally to what we call the continents. So here it's important to make this difference because I'm going to talk about continental crust and continents through the talk. So for me, the continents are the emerged part of continental crust. So today, both the two are similar, but it might not have been the case in Earth's history, all through Earth's history. So the continental crust and the oceanic crust are also very different in terms of ages. So the continental crust have rocks of almost all ages, up to 4 billion years, while the oceanic crust is younger, with a maximum age of about 200-300 million years. They are also different in terms of thicknesses. So it's quite thick for the continental crust, 30 to 50 kilometers, and quite thin for the oceanic crust, usually less than 10 kilometers. And another important difference is their mean chemical composition. So I'm showing here only silica, but there's also a lot of differences in other elements. But basically, what we know today is that the average composition of bulk continental crust in terms of silica is about 60.6 or 61 weight %, which make it felsic, okay, on average, while the oceanic crust has an average silica content of about 51 weight %, which make it mafic. So in detail, the structure, the vertical structure of the crust is a bit more complex. It's not of the continental crust, sorry. It's not a homogeneous crust. It's in fact vertically stratified. So it has been estimated that the silica content of the crust varied with depth, and that we have basically a more mafic lower crust and a more felsic upper crust, which vary quite on a large range, which is about 53 weight % at the base, up to 67 weight % in the upper continental crust. And there's a lot of models that suggest that this chemical variation of the function of depth directly reflect the way the crust is formed. So basically, mostly mafic melt directly extracted from the mantle at the base. And then the crust goes through several melting and differentiation events, which is what I show here by this arrow, to reach much more evolved composition, which are more felsic on the level, on the upper level. So this is very important to understand this, because when you use sedimentary rocks to try to understand what's going on in the crust and try to estimate the composition in the crust, you in fact sensitive to only the upper level, because this is what is eroded and then form the sediments. So it means that we're going to be seeing only this upper very felsic levels, and that we are not sensitive to what's going on deeper. So this is a bias, of course, but you have to keep that in mind, and this is something that we need to take into account while interpreting the data. This is not a big deal, because you can always make the assumption that if you keep the same stratification through all Earth history, then if you manage to get information on this one, you can assume that it's pretty much the same at the bottom. Well, this is just an assumption, of course. Today, we also think we know how the crust is, the continental crust is produced and destroyed. And according to several studies, continental crust is mostly formed and destroyed in subduction zones. Okay, you have here a diagram showing you with the blue numbers the volume of crust that is produced in different tectonic settings. So you have subduction, hotspot, collision, and extension. And the amount of crust that we think are destroyed in cubic kilometers per year, these are the orange numbers. And you can see that the highest numbers are in subduction zones. There have been 7 mass balances done through the past 20 years, I would say, even more than that. And in general, people think that it's quite well balanced at least for the past 300 million years. So we have an amount of crust generated that is about equal to the amount of crust recycled, meaning that the volume of crust was probably constant because you produce as much as you recycle in the past 300 million years. So this is what we know about the continental crust today. When I mean today, I mean the past 200 million years, of course. But there is a lot that we don't know about the history of the continents. The first thing that is a matter of debate is the composition of this continent through time, so the emerged part of continental crust. And there have been several studies that have very contrasting results. So this study here in Science in 2016 that was based on trace element ratios in sediments concluded that the crust, the continental crust, was probably mafic in the Archean, and then so mafic here you can see that it's mostly made of basalt in black, and then cometites in green. And then there is a transition at the end of the Archean, beginning of the Proterozoic, 2.5 billion years, or between 2.5 and 3. Towards a crust that becomes very much felsic and looks like the one we have today, with a larger proportion of felsic lithologies in it. The second study, 1 year later, used titanium isotopes in sediments to conclude that the crust was felsic in the past 3.5 billion years, and that there was no major changes in terms of composition through time. So this is very different results. And this has also consequences for other related studies, because, for example, this change from mafic to felsic composition is sometimes taken as an evidence for the start of plate tectonics. So whether this change happened or not is very important to determine for example, to try to understand how plate tectonics work through time. The second big problem about big debate we have about the history of continents deals with their growth through time. Basically, whether we had not a lot of continents in the Archeans, and or how does that evolve through time, whether we had very quickly a lot of continents or not. And so we have also all these different models that has been suggested for the growth of continental crust. So I'm not going to add another curve to this diagram. I think there are already enough. But the thing that we can say is that it's not well constrained, and there is an underlying question here that is whether the volume change, okay, but whether the growth is continuous or happened by pulses, because this makes a big difference in terms of processes to generate new continental crust, whether this is something that is continuous through Earth's history. So continuous means whether it can be quick at the beginning and then slow. But if it's not, it could be by pulses, that is to say, really like periods of times when you produce more crust than others. So this is these two questions that I would like to address in this talk. And most of the time, the growth of continental crust is addressed through the zircon records and through the analysis of uranium, lead, and hafnium isotopes. So I'm showing here two plots, showing here on the top the distribution of uranium, lead ages in zircons. Okay, these are compilation from 4 famous papers. And you can see that there are peaks and troughs in this diagram, okay, that have been interpreted in different ways. And here you have the hafnium isotopic composition of zircons. There's a lot of data that has been measured through time. But the thing is, when any of this data point here in this diagram, or this one, in fact represent a very in situ analysis. So it means that this is a piece of zircon grains, so usually 10 to 50 nanograms, okay, zircon grain that has been taken out of sediments in one sample locality. So you need a lot of this data, and even if we have a lot, to make sure you're not biased by the location or any singular event to make interpretation at the global scale. The advantage of using neodymium isotopic composition, this is what I used here in this study, is that these are bulk analysis. So it means that you're taking a sediment for one sampling location, you're taking all the grains in that. So this is about 100 milligrams of material, meaning 1,000,000 times more material than what you're probing with the in situ analysis in zircons. And then this analysis is already an average of the composition of the continental area that is drained here. So by one analysis, you get the average composition of a large continental area at any sediment deposition time through Earth's history, which is quite interesting. You need much less point than what you need for zircons. The other very interesting thing is that the samarium neodymium isotopic composition of sediment is not fractionated by sedimentary processes, meaning that the composition of the sediment that you measure is assumed to be similar to that of the crust. Okay, there is no change of this concentrate of this composition through the transport of the sediments or the making of the sediments, and this is something that has been studied a lot and now shown that it's quite reliable. So of course, I'm not the first one to think about using neodymium isotopic composition of sediments to try to understand the history of continental crust. There have been several studies, mostly in the 80s, that tries to look at the neodymium isotopic composition of sediments through time and try to say something about continental growth. But these studies were mostly focused on trying to get volume of crust. And I decided to look at the compilation, at the data with another view. So I started to make new compilation of samarium neodymium data because there were much more data than previously in the 80s. And you have here just the distribution of the data that I'm using in the model, the isotopic models. So the number of data used versus the age of the sediment, such as the stratigraphic age. And what I did is like I compiled the data for both fine grained in gray and coarse grained sedimentary rocks to see the potential effect of sedimentary rocks, of grain size. But I'm not going to talk about that today. Anyway, there is no difference between the two records. So this is something that the important point here. So these are 2,500 data. Several statistical tests suggest that the most appropriate binning given the initial distribution is about 200 million years. So this is what I decided to do through the whole studies. And of course, I have looked at the data to reject any weird measurements or any ratio that was not normalized to the right value. Okay, so with this database, I decided to explore two things. First, the composition of the continents. What does these sedimentary records tell us about the composition of the continents over time? And I'll show you that we can use the samarium neodymium ratio of the sediments to average the silica contents of the, silica content of the continents for time. And then the second part will be more about continental growth. And I'm going to try to show you a modeling approach using neodymium isotopes to not to constrain the volume of crust, because I think this is something that I cannot do with this database. It's just under constrained. But instead, I will show you that we can extract relative proportion of juvenile crust through time, and this has implication for the way the crust was formed through time. Okay, so let's start with the first question. So maybe some of you are not very familiar with sediments and sedimentary sorting through time. So the first thing is I wanted to say that it's not that easy to get to the silica, the average silica content of the continent using sediments, because basically the silica content is fractionated through the transport. So if you look here at a vertical section in a river, you will see that there are some material that are transported as bed load, other as suspended load, and this basically depends on the size and the density of those materials. So you tend to have coarser fractions at the bottom, which is the bed load, and then finer fractions in the suspended load. And this generates a mineralogical sorting in the columns. And so if you look at this chemically speaking, you can see basically if you sample sediments here, suspended load here, and suspended load at the bottom, then the silica content vary a lot with depth. Here 55% up until 75% at the bottom. And the counterpart is true also for other elements such as aluminum, because of course you have less clay in the bottom and more clay here. So if you look at the silica content of the sediments, this will not reflect the silica content of the source because it has been fractionated. And so another way to say that is like if you erode a granite with an average silica content of 70 weight%, you erode, alter, transport this material, then you can form a shale that has a much lower silica content and a sandstone that has a much higher silica content. So you cannot use this proxy to get to the initial composition of the source. The good thing is that the samarium neodymium ratio is not fractionated by sedimentary processes, meaning that if this initial granite has a samarium neodymium ratio of 0.12, you will find the same ratio in both the two products independently of their grain size. And this is an important process, all the more that when you look at another compilation, this time in igneous rocks, you can see that in igneous rocks, the silica content is well correlated with samarium neodymium ratio. So to say it quickly, a basalt or a mafic rock will be characterized by low silica content and relatively high samarium neodymium ratio, while something that is more felsic will be characterized by higher silica content, of course, but also lower samarium neodymium ratio. And there is a quite nice correlation that we can regress and calculate here. And so what I did here is that I used the samarium neodymium ratio of the sedimentary rocks through time to convert it to silica content using here this equation, this regression that I have in igneous rock. So here I'm showing the samarium neodymium compilation of sedimentary rocks, okay? In the first panel here, so you have the binned average in pink and the moving average in purple. This is just to show that the two types of averages are given the same responses, okay? So it's not sensitive to the way I'm calculating the averages. And so then I took this record here and used the equation, this trend defined here, to convert the samarium neodymium ratio of the sedimentary rocks into silica content, which I assume is the average silica content of the emerged continent. And this gave me this record. The yellow field here is the 95% confidence interval. And the main thing that you see here is that there is not a lot of variation, okay? The modern upper continental crust composition is shown by the orange line here, plus or minus 2 sigma. And so at the first C, you can see that the conclusion is that the silica content of the continent has not changed through the past 2.7 billion years. As a comparison, the modern basaltic crust, oceanic crust, would be at 50, so something here, like here. So the thing that we can say is that the sediments that I compiled in this database, so all the sediments I found with neodymium data, did not sample a crust that was mafic, Otherwise, we would have a value around 58% if it was fully mafic, I would say. There are some peaks here that are in fact related to the number of samples that I have here. That is to say, not a lot, but within the uncertainty, they fully match with this record, with this very constant composition. So this is the conclusion for this first part. Continents have always been felsic in the past 3.7 billion years. We can, I think, say with relatively high confidence that the neodymium isotopic record of those sediments show that the silica content was always higher than 68%. And this is in agreement with what Greber et al. Found in Science with titanium isotopes in shale. Okay, they found that there was a very, very small variation through time. Then also in agreement with a re-evaluation of the meaning of trace element ratio in sedimentary rocks in a relatively more recent paper in 2020, when they tried to show that all trace elements basically points towards bulk silica crust that has not changed a lot through time. Okay, so now if we go to the second topic, which is the growth of continental crust. So this time I use the neodymium isotopic composition of the sediments through time. So here is just the compilation of the data I have done. So we have the neodymium isotopic composition were calculated at deposition age versus the age of the sediments. The average, the bean average in pink, and the moving average in purple. And the modern crust is here, so they're really well matched, which is other. You can see that the mean isotopic composition has changed through time. It has become less and less radiogenic. And this is consistent with what we think is the continental crust through time. That is to say, a mixture between juvenile crust, that is juvenile crust, so it's new crust directly extracted from the depleted mantle, and old crust, so not necessarily something that has been formed 3.8 billion years ago, but old crust. And so this means that at any point T of Earth's history, you can basically see the crust as a mixture between a new contribution from the depleted mantle and a mixture and something that is already formed from some time. To go a little bit further and try to quantify this proportion, to know how much new crust was formed through time, I did a model that is in fact quite simple. It's a mass balance, where I assume that at any point T of Earth's history, the average neodymium isotopic composition of the crust is the result of a contribution from the already existing crust. So this is what is shown in gray here, plus a contribution from the juvenile crust, minus the contribution of what is lost into the mantle, which is the recycled crust. I'm showing here plate tectonic models, right, with subduction, collision, and stuff. But in fact, there is no assumption of geodynamical model in this equation, and you could recycle the crust by delamination or form the juvenile crust in any other tectonic setting. This would not change the calculation. So when you do that, if I show you what it does in this type of diagram, you end up to model a reworked crust. And basically, each time the true composition of the continent, which is represented by sediment in pink here, so each time this pink composition deviates from the reworked crust, it means that you have added something new, okay, which is this composition. So you can quantify how much juvenile crust was added at each point T. So each time you have this big vertical deviation, it means that you have a high proportion of juvenile crust added. So this is what we see here. I think I put the yellow bands here. And so through time, we can reconstruct the relative proportion of juvenile crust, so new crust extracted from the depleted mantle. And I found that there are at least 6 periods of time during which the proportion of juvenile crust are higher than they should have been if there was no production. So these 6 periods of time correspond to the vertical yellow bands here. Okay, so this is what the neodymium isotopic composition are saying. Now, how do we interpret that? So it either means that there are pulses in the production of juvenile crust through time, but it could also be that this is a bias of the record. So either a preservation bias or a sampling bias. And in the next slides, I'm going to explore these 2 possibilities and in fact try to show you that this is not possible, that this results from a bias and that this necessarily corresponds to pulses. So the first type of possible bias is the preservation bias, which has been first suggested by Oxworth et al. For the zircon record. Basically, the idea is that you produced a constant amount of juvenile continental crust through time, but because you erode this differently at different periods of time, you are able to preserve only very well the zircon produced at some periods of time. And this is the reason why you end up with this present-day distribution with peaks during a certain period of time. But this does not reflect pulses in the production of juvenile crust. This is just a preservation issue. Okay, so that might be the explanation for the zircons, but I think this is not a possible explanation for the neodymium isotopic record, simply because when you look at the initial distribution of the data that I used into the model, I do not have the same peaks and throws that the results are showing. So if I had the preservation bias because I had preserved more preferentially these or these terrains, then I should see, I think, a correlation between these 2 records, the juvenile crust production and the distribution of the initial data, and I'm not seeing it. So for me, this means that this preservation bias is not a possibility. So I don't think this happened. The second type of bias is a bit more complex. This is a sampling, what I call the sampling or the erosion bias. And this is basically the preferential erosion of juvenile crust in high relief area. So this has been suggested by Allegre and Rousseau in the 80s, 84, I think the first time this was mentioned. And this type of bias is based on the assumption that juvenile crust is preferentially exposed in a high topography area. And because this high topography area are the areas that produce most of the sediments on Earth, this is what is shown in this map. You have the colors correspond to the sediment yield, and you can see that the highest sediment yields are in red, and they generally correspond to the mountain belt, so the Andes here, the Alps, the Himalayas, of course. And so this means that if you have more juvenile crust, as suggested by Allegre and Rousseau, in these areas, then you might, in fact, overrepresent the juvenile crust in the sediments. And so the sediments the composition of the sediments might not be representative of the crust as a whole, but might be biased by there may be too much juvenile crust in them. So this is a concept that was not really tested at the scale of the global sedimentary system. I think this is really a concept that was theoretical. And so I decided to look at another database on the sediments that we have today to see whether we could find evidence for this potential bias. So I compiled the neodymium isotopic composition of modern river sediments this time. I would say river sediments that are just exported to the ocean at the mouth of large rivers. And I looked at a database of about 1,500 rivers. And I took the one that has the biggest drainage basin or the biggest sediment load, because you can have like a small island with high topography So a small drainage basin, but a lot of sediment generated. So I didn't want to be biased by either the basin or the load. And so I decided to take either this one or this one. And I ended up with 67 rivers. And I was able to find the neodymium isotopic composition of 49 out of the 67 rivers. So I think this is quite representative of what's going on in the sedimentary system today. And when you look at this data, so each point is a river, you can see that their sedimentary load, so delivered to the open ocean, basically, correlates pretty well with their maximum elevation, which is taken here as a proxy for topography. So what this means is that when you have a high topography in the drainage in the catchment area, then you produce a lot of sediments. This is the case of Ganges, Brahmaputra, Indus, or the Amazon. And so you are not biased by, because one possibility is that this sediment load is biased by human activities, but here it's seems quite normal with what you should expect from the catchment area. So if we have this bias I was talking about, or the bias mentioned by Allegan also, you would expect that the rivers that has the highest sediment load has also the most juvenile composition, if juvenile crust is preferentially exposed in high topography area. So you would expect this trend with epsilon neodymium, the isotopic composition of neodymium. And this is what you get. So you get no correlation at all. At least not something like this. Maybe you have something like this, but this is another story. Well, I would say no correlation at all. And if you take the average composition of all these rivers, which are the green bars here, you end up with an average value that is really similar to that of modern upper continental crust in orange, plus or minus 2 sigma. And so basically what it means is that the average composition of river sediments is quite well representative of that of modern upper continental crust, and there is no significant bias in the neodymium isotopic record today. So there is no reason to think that there is a bias through Earth's history. So this led me with the only possibility that I think is explaining the peaks here, which is that the highest proportion of juvenile crust necessarily reflect pulses in the production of juvenile crust through time. So now the question is, how do you explain these pulses? I'm not going to give you an answer here because I think we do not have, well, we cannot really say why, but we can try to understand. The first thing is that there are many people that have suggested that episodic continental grass could be linked to superplume activities. So this is the case of the model of Stein and Hoffman here, or this one in Arndt and Davai, where the episodic formation of superplume would accelerate plate tectonics and then generate rapid subduction and then more production of continental crust. So I tried to find a correlation between the peaks that I was seeing in the growth record and the large igneous provinces, which are supposed to be the product of superplume activities. So you have here the results of the study of, I was talking, the study we have been looking at here. And here you have the records of leaps even through time. Okay, the number of leaps even through time. And here the potential leaps intensity, which is shown by the potential reconstituted area of leaps produced through time. And you can see that there is no obvious correlation between these two leaps records and the continental crust record. So it does not go really towards a consequence or cause effect. And another argument is that the periodicity of leaps and their duration is not very consistent with what I found here, because here the periodicity of the episodic growth is mostly around 500 to 700 million years, so not in line with the periodicity of leaps record. Instead, this periodicity is more in agreement with the supercontinent cycles, okay? So the supercontinent cycles are not very well defined, but here is one estimate among others, where you have an estimate of the potential mountain building event that correspond to the assembly of supercontinents. So these are the black bars. And the periodicity is more consistent. The timing is not super well defined. Also in my study, the beginning is about 200 million years, so it's difficult to correlate the two. But what I would point out is just that the periodicity and the duration is more in line with supercontinent cycle than compared to superplume activity, I think. And I like to show this study from Coltis et al., where they actually build numerical models to try to explain the supercontinent cycles. And so what they found is that when they do not force the model to anything, they realize that in fact the speed of plate tectonics pretty much vary naturally through the supercontinent cycles. So there are periods of time during which the plate velocity is super slow. These are shown by the the small arrows here everywhere on the Earth, and associated with very a low number of subduction zones, while there are some other periods of times where there are some acceleration in the plate velocities because the drag forces are changing. And then you have more subduction zones. So what I would like to just maybe suggest here is that the episodic growth of continental crust might be just the normal expression of the supercontinent cycles. There is no need to involve catastrophic events such as the superplume activities. And these variation in plate velocities through basically the formation of large amount of subduction zone could explain the variability that we see in the production of continental crust. I would say naturally, just the natural expression of plate tectonics, in fact. Okay. So as a conclusion slide, I just wanted to show you the two main results, in fact, of this study, based on the compilation of Simurium, neodymium, isotopic composition of sedimentary rocks. The first main conclusion is that this record shows that there is no significant variation of this average silica content of the continent through time. Okay, they have always been felsic in the past 3.7 billion years, according to this record, of course. And the second main result is that this shows that the production of juvenile crust was episodic and not continuous. So it's not clear why it is episodic, but this is something that we will have to take into account in the future interpretation. For me, this is quasi impossible that this is a preservation of a sampling bias, as you can see, as we can maybe suspect for the zircon record. And the thing that I wanted just to mention is, like, maybe we do not need a catastrophic event to explain this. It could be the result of plate tectonics and be episodic. It doesn't have to be necessarily continuous if it's plate tectonics. Okay, and with this, I'll thank you. And if you need, or if you want to look deep more into the models, you can look at the papers that has been published at the end of last year. Thank you.
Okay, great. Thank you very much, Marion. Now's time for question from our participants. So feel free to open your mic or leave your question in the chat, and I could read the question on your behalf. Okay, let me ask questions. Oh, okay, there's another one. Okay, I'm going to read the question first before I ask my own. Okay, so Umigash asks that there are two sharp changes in silicon dioxide content at 3 billion years and 3.5 billion years. Can that be due to the sampling bias?
Yes, this is, so this is a sampling bias in the term that it is much more preservation bias, but not a sampling bias in the terms of isotopic bias. So when, of course, this highest uncertainty here are linked to the fact that we are looking at 1 or 2 Archean terrains, okay, older than 3 billion years. There are not a lot of areas on Earth. And so here you have a large variability simply because you do not have a lot of samples to work with. So this is, okay, this is, I would say, a third type of biases, but that has no implication on the potential peaks here. I mean, if you have 3 or 10 samples, this will not change the size and the location of the peaks here. But it's true, when you are older than 3 billion years, it becomes, yes, much less constrained because of the smallest number of samples we have.
Okay, actually, I have a, okay, that's the other one jumping up now. Okay, so Trinas asks that, so for the 200 million beings, will that affect your results? Is it possible to get a more Sirium medium data to reconstruct the silicon dioxide over time?
So the bean has no impact on the data. So they are in the supplementary file of the paper. We tested not several beans, but the moving average, for example, which is basically the same. The thing is, so the 300 million beans has been constrained by statistical tests so that we have enough data per bin to say something about an average. But I've tried, of course, 100 million years or 50 million years. Basically, this is the same information, but there are some beams that are empty. So, and some of the beams are not statistically resolved because there are 2 data in it or stuff like that. So the only way to resolve this is to measure again and again more and more samples, and then go back to this in 10 years and add samples. I think this is really interesting for the Archean stuff, of course, even if I do not see how you can basically go to something very, very mafic. Well, we are very far from that here, but yeah, the only way to have a more temporal, well, how would you say that? Yeah, be more precise on the time would be to add more data.
Okay, so I have a curious question that in terms of your one of your plot showing the elevation as well as the erosion relationship, for that one for different rivers in the world. So by that the sediment load, I'm curious that do you think that the human activity that has a great impact on the sediment load? Because I believe that for almost all the rivers in the world are heavily impacted by that. And since you draw, especially when you draw this correlation, I buy it, especially for the larger ones, the Amazon, Indus, Ganges, for example, they are the ones that with a lot of sediment loads. But for a lot of other points here, it doesn't look, like say, with a low elevation, doesn't seem to show a clear trend of increase of sediment load with the elevation.
Yeah, this is certainly messed up by the human activities for sure. But so the compilation, it's a book actually of 1,500 rivers where they try to compile all the data about the rivers on Earth. They try to report the parameters, so not only the sediment load, but a bunch of other things without, or trying to remove the human impact. So they were based on measurements that were done early in the 50s, for example, before they construct the dams and stuff everywhere. But of course, there is a large, probably a large part of messing on this trend that is due to human activities. And also the maximum elevation or the topography is not the only parameter that influence the sediment load. You have also, for example, climate, the rainfall. I think this is the second one. And then you have other parameters. There is also, of course, the drainage area that plays into this correlation. So I think most of the noise here is due to that. But I'm not the one saying that the correlation is nice here, because when you look at the paper that I'm trying to find what is the main proxy that control the sediment load, they all have this type of diagram. Okay, this is not my compilation, in fact. And they say, well, with all we have, when we correlate, when you do a biplot with sediment load and another proxy, the nicest correlation is this one, correlation with the relief. So I think this is the best we can have, but I agree with you that yeah, it could be difficult to find a correlation here.
Okay, thank you. Next question, please. So Umi Gash asks again that in case of bulk analysis, if there are multiple sources of sediments, can the azeotropic ratios be affected due to mixing?
Mixing between what and what? You mean when I look at the bulk neodymium isotopic composition of sediments? Is that the question? Is that a reference to this figure? When I said that this is quite well representative of the continental area.
Umi, is it possible for you to open your mic and clarify your question?
Yes, that's what I was asking, that because we are taking a sample, like because like this sediment can have multiple sources, like two different cratons or two different sources. So in that case, will like they'll have different isotopic composition. So how would we like understand if there is a mixing or not?
Yeah, exactly. In fact, this is exactly what I'm doing. It's like I'm assuming that so when you get the average composition of in any bean time here, what I'm assuming that it's always a mixture of something old and something young. Okay, so it could be when I say something old, it could be two cratons of different ages, but on average, if you erode a craton of 3 billion years and then another one of 2 billion years, then it gives you an average age. So this is what I call the old crust. So this is a model at the global scale. So of course it is completely wrong at the local scale. But basically what I say is that you can calculate the average age of the existing crust at any point t, which is what I call the reworked crust here. And this is supposed to reflect the average age of the existing crust at the time of the sediment formation. So in fact, in this way, you take into account the possible mixtures of different old cratons, and then this is what I call the reworked crust. And then you have another contribution, which is the new crust, which is what we try to constrain here. And so you can do the mass balance to determine to quantify basically how much new crust you need to put to get to this pink composition while you're supposed to be there if you erode just old crust. So this is taken into account into the model, but of course not at the local scale, assuming that you're looking at the stuff on a global basis. But in general, I think this is not a very big assumption, because when you look at almost any sediments, modern sediments today, you'll get an age of 2 model age, an edema model age of 2 billion years. And the average composition of the sediments, so modern ones, which is the one here, is -10, and this is exactly the isotopic composition of the crust. So it means that this is a pretty good, in fact, the sediments today, when you took the average composition of the sediments, you get the average composition of the crust. So
Thank you.
you're welcome.
Okay. Do we have more questions? If not, I think we could finish our webinar today. So almost 1 hour. So thank you again, Marion, for giving the talk. And thanks everyone for your participation. And our next webinar will be a week from now. So I will see you then. Okay, thank you, Marion. Have a good day.
Thank you very much. Bye-bye.